Hey, welcome to The Explainer. Today, we are cracking open the programmer's toolbox to talk about something that is truly the fundamental building block of any efficient code: data structures. They're kind of the invisible architecture behind every single app you use. I mean, have you ever stopped to think about it? How does an app like Spotify find that one song you're looking for out of, 80 million tracks? And it does it in like a split second? Or how does Google just instantly pull up exactly what you were looking for? It really feels like magic, right? But it's not. It's just really, really good engineering. And the secret sauce behind all that incredible engineering? Well, you guessed it, it's data structures. That's the whole game. They are the specific, totally deliberate ways we organize information to make these insane speeds even possible. All right, so let's get into it. The absolute best way to think about data structures is to picture a toolkit, like a set of specialized tools for a craftsman. I mean, you'd never use a hammer to turn a screw, right? Well, in programming, it's the exact same idea. You never want to use the wrong data structure for the job you're trying to do. So what are we actually talking about here? At its core, a data structure is just a way to organize and store your data. But the key thing to remember is that it's designed so that the data can be used efficiently. And each format, each one of these tools in our kit, it has its own unique set of strengths and, of course, weaknesses. And here's why you should care. This is the big so what. Choosing the right tool for the job, it doesn't just make your program run faster, and that's the better performance part you see here. It also makes your code so much cleaner, more logical, and just plain easier to understand for you and anyone else who looks at it. So the point is, this is about both speed and simplicity. It's a win-win. Okay, let's start with maybe the most straightforward tools in our kit, the linear structures. And the name kind of gives it away, right? These are all about organizing data in a sequence. One item, then the next, just like a straight line. First up, we have the array, the classic. Just picture a numbered row of boxes all sitting right next to each other in the computer's memory. They're contiguous. And because they're in this predictable, unbroken line, if you need to get to, say, box number 500, the computer can just jump straight there. No searching needed. That's exactly what we mean when we say instant index-based access. Now, this slide is super important because it shows the trade-off. Check out that O1 for array access. In programming terms, that basically means instant. It's incredibly fast. But look at what happens when you try to insert or delete something, especially at the beginning. It's ON, which is slow. And why is that? Well, if you want to add a new item at the very front of the array, you literally have to pick up and shift every single other item over one spot to make room. The more items you have, the slower it gets. And this problem, well, it's exactly why our next tool exists. So let's talk about the linked list. Instead of that rigid line of boxes, I want you to imagine something more like a treasure hunt. Each item, which we call a node, holds a piece of data and a clue that points you directly to the location of the next item. So if you want to add a new item at the beginning, easy. You just change the very first clue to point to your new item. It's unbelievably fast for that one operation. But here's the trade-off, right? To find the 500th item, you have to follow 499 clues to get there. There's no skipping ahead. All right, next up, we've got two special kinds of linear structures: stacks and queues. A stack operates on a last-in, first-out principle, or LIFO. The absolute perfect analogy is a stack of plates. The last plate you put on top is always the first one you're going to take off. A queue, on the other hand, is the total opposite. It's first in, first out, or FIFO. And for this one, just think of a line at the grocery store. The first person to get in line is the first person who gets to check out. Simple as that. And believe me, you use these things every single day without even thinking about it. Ever hit undo in a Word doc or a Google Doc? That's a stack. It's just popping the last action you took right off the top of the list. Or how about when you send a document to a printer? It goes into a queue, just waiting its turn in a nice, orderly, first-come, first-served line with all the other print jobs. Okay, that's great for things that fit in a line. But let's be real, not all data is that simple. What about more complex relationships? For that, we need to pull out our nonlinear structures. These are the tools we use for representing things like hierarchies and big interconnected networks. And the first one we'll look at is the tree. It's the perfect structure for anything that has a hierarchy. I mean, just think about the file system on your computer, right? You've got a root drive, and inside that you have folders, and inside those folders are more folders and files. That's a classic tree structure. Or think about a company's org chart. Same idea. Now, there's a special kind of tree called a binary search tree, and it has a legitimate superpower. It keeps its data sorted at all times, which allows for ridiculously fast searching. This O of log n thing you see here, what it means is that even if you double the number of items in the tree, it only takes one single extra step to find what you're looking for. To put that in perspective, for 1,000,000 items, it might only take 20 steps to find anything. It's just mind-bogglingly efficient. But what if the relationships aren't a simple top-down pyramid? What if everything can connect to everything else in a big web? For that kind of problem, we need a graph. A graph is really just a collection of nodes, you can think of them as dots, and the edges, which are the lines that connect those dots. Its entire job is to model complex, messy relationships. And when you start looking for them, you realize graphs are absolutely everywhere. I mean, they are the hidden backbone of our digital world. Your friends on Facebook or followers on Instagram, that's a social graph. The entire road system in Google Maps, with cities as the nodes and roads as the edges, yep, that's a graph. The very fabric of the internet itself, with websites linking to each other, you guessed it, one massive, sprawling, interconnected graph. Okay, so we've seen tools for ordered lists and tools for complex networks, but now, let's talk about the undisputed champion of pure, raw speed when it comes to just finding a piece of data. Let's talk about the hash table. Seriously, a lot of programmers will tell you this is the single most important data structure of them all. The basic idea behind it is actually pretty simple. It stores data in pairs. You have a key, which is what you use to look up a value. The best analogy is a dictionary. The word is your key and the definition is the value. And hash tables are engineered from the ground up to make that lookup process happen almost instantly. So how on earth does it get that speed? Well, it uses this really clever trick called a hash function. So you give it your key, let's say it's a username. The hash function takes that username and, through a bit of math, it instantly converts that key into a number. And that number is the exact index in an array where all of that user's data is stored. See? There's no searching involved at all. It's just a direct calculation. And the result of that clever trick? 01, constant time. On average, looking something up, inserting a new item, or even deleting an item from a hash table takes the same amount of time. It flat out doesn't matter if you have 10 items or 10 million. The speed is, for all intents and purposes, instant. And that right there is a complete game changer in programming. So it's no surprise, right? Because of this insane speed, hash tables are used everywhere. They are the engine that powers Python's dictionaries and Java's hashmaps. They're absolutely fundamental to how databases index information so you can find records quickly, how websites use caching systems to load in a flash. The list goes on and on. So there you have it. We've looked at the whole toolkit. We've got tools for simple lists, for hierarchies, for complex networks, and for lightning-fast lookups. The real art of being an efficient programmer, the real skill, is knowing which situation calls for which tool. And this slide right here, this is your key takeaway. Seriously. Think of this as the cheat sheet for your entire programming toolkit. Need to look up users by their unique email address? That's a classic key value lookup. Grab a hash table. Need to build an undo button? That's a last in, first out problem. You want a stack. Modeling a social network where it's all about who knows who? That screams relationships. You need a graph. It's all about matching the problem to the right tool. So I'll leave you with this final question to think about. Imagine you're tasked with building the next big social network from scratch. Knowing what you know now about this amazing toolkit, what data structure would you reach for to store the most fundamental piece of the puzzle? The massive, interconnected web of friendships. The right answer and the success of your app all comes down to choosing the right tool for the job.